If you remember, we have solved this problem using the Km equations. So we have an infinite plate and we have a crack here of length 2a, and the crack is subjected to crack face tractions. I have drawn them normal here. We have also done it for the shear crack face traction. And this is what we call the Griffith problem. Now, we can have another problem where we have again the infinite plate, the same crack. Now there are no crack face tractions, but we have the same. So this, let's say that we call this sigma infinity, the normal stress. We have the same normal stress applied at the remote boundaries. This is also called the Griffith problem. So we are going to show in the next problem that these two are kind of equivalent problems, and if you know the stress intensity factor for this, you know the stress intensity factor for this as well. Why is that? Is because of the principle of superposition that applies to certain situations in linear elastic fracture mechanics. Now, uh, what is the relation between the two? So we can start with a plate, infinite plate without a crack, but subjected to a remote normal load, sigma infinity. So this is a symmetric loading, and the stress everywhere inside this body is equal to sigma infinity. So the stress matrix is 0, sigma infinity, 0, 0. Everywhere in this, it's uniform, homogeneous over the um, whole plate. Now, this problem can be thought of as being equal to this problem. In this problem, we have a crack. Here there's no crack. You have a crack at some location where the stress is this, and then we apply the opposite stress to this crack. So in, this is the stress state at the location of this fictitious crack, and we have applied a stress of this at the location of the fictitious crack. This stress, this stress that we have applied obviously closes the crack, and there is no singularity that arises at the crack tip. So the crack tips are no longer singular because they are closed by this stress field, which is the opposite of this stress field. So this problem does not have a crack. This has a crack, but is closed by the stress that exists at the location of the fictitious crack in this problem. So these two problems are equal. Now this problem can be broken up into two problems. One is where this crack is not subjected to any compressive loads, is not closed, and has sigma infinity applied at the far off boundaries, plus minus a problem where sigma infinity is tensile and applied on the crack face. So if I wanted to use plus here, I would have used sigma infinity like this. So this plus this would exactly be this problem. So I have broken this problem up into a problem without crack face tractions and with the compressive crack face tractions. But this is not, I could have done this. Instead, what I did was I used tensile loads and used a minus here, which means that this problem and this problem is equivalent to this problem minus this problem. And this problem is what I want to solve. I want to solve the problem of a crack subjected to remote normal loads. For this case, the stress intensity factor is obviously zero, as it is in this case. In this case, there's no crack, so there's no stress intensity factor. This is equivalent to this, so stress intensity factor in this case is zero. Stress intensity factor in this case is K1, which we want to find out, and stress intensity factor in this is equal to K2, which we know is sigma infinity root pi a, where 2a is the length of this crack. 2a is the length of this crack. We have already derived this from the Km equations. Therefore, 0 is equal to K1 minus K2, which means K1 is equal to K2. Therefore, for this problem as well, the stress intensity factor is the same as this problem. So that's why both are Griffith problems. This problem and this problem actually have the same stress intensity factors, though obviously they don't have the same stress fields all over the body. The stress fields are different. Here the stress fields die down to zero as you reach the boundary. Here the stress fields tend to sigma infinity as you reach the boundary. So the stress fields are not the same. But when you look at the stress field close to the crack, then both these stress fields are governed by the same stress intensity factor, which is sigma infinity root pi a. So the stress intensity factors in these two cases are the same. In fact, the principle of superposition can be used when you have two problems of the same mode and you want to find the stresses ahead of the crack tip. So look at this problem. Look at this problem. So in this problem, the crack is being opened by two. There are two. This is part of a cylinder. This is part of a thick cylinder, which has a crack like this. So if you look at the cylinder, if you look at the cross section, it's long plain strain cylinder. There is a crack here that runs along the cylinder. Okay, this is the crack, and this crack is shown here. Now there are two contributions to this crack. This is a mode 1 crack. Firstly, because there is a hoop stress on the cylinder walls. There's a hoop stress sigma theta theta, and that sigma theta theta is P naught R by T if this is a thin cylinder. So sigma, so on this there is a hoop stress. Sorry. So in the region around the crack, there's a hoop stress here, which is so this is the remote stress of the crack, and that is what is shown here. So the crack is opened by this hoop stress that acts because of the pressure inside. But then there is also a possibility that if this pressure is caused by a fluid, that fluid seeps into the crack, and causes a pressure on the crack face, which is normal to the crack and equal to P naught. So the crack here is opened by two contributions. One is due to fluid inside that has seeped into the crack and is applying a pressure P naught on the crack faces, and the other is due to the hoop stresses that are caused and is trying to hoop stresses that act as remote stresses for this crack and are trying to open it. So the total stress intensity factor in this case can be found out by stress intensity factor due to this problem, which we call K1, and this problem, which we call K2. So the stresses ahead of the crack tip, if you want the stresses ahead of the crack tip, very close to the crack tip, then the stresses would be K1 by root 2 pi r sigma ij hat and K2 by root 2 pi r sigma ij hat. Here, before you superpose, you should take care of a couple of things. You can superpose obviously the same component of stress only, because these angular functions are dependent on which component of stress you are looking at. And the second thing, these angular functions are dependent also on the mode. So you cannot, in this case, this is causing a mode 1 opening of the crack. This is also causing a mode 1 opening. So both of these are the same modes which are being superposed, and these angular functions also depend on the mode of opening of the crack, mode of deformation of the crack. So both of these are mode 1. So this angular function and this angular function are the same, and therefore in this case you can add them together. You could not have added them together if one was causing mode 1 and the other was causing mixed mode, or mode 2. So you have to remember that you can superpose stress intensity factors, but you can superpose stress intensity factors only if you are looking at the same component of stress and the same mode of the crack. So leak before break is a very important concept in fracture mechanics. In fact, it's a design philosophy which can be called fail-safe design. So, like we discussed at the beginning of this course, that uh, one way of designing on the basis of fracture could be to accept that cracks flaws exist and the flaws will grow, but then uh, before the flaw causes catastrophic failure, we want to get some indication that a catastrophic failure is imminent. So from that point of view, leak before break is a very important design principle for pressure vessels, pressurized pipelines, and so on. So here is an example of a pipeline failure where a crack has grown along the length of the pipe and split it open into two. Here are some more examples. Maybe a crack started somewhere here, then grew along this pressurized vessel, grew along the length of this pressurized vessel, and caused catastrophic failure, as it did in this case. So these are the kinds of situations that we want to avoid. We cannot avoid uh, failures, but what we can avoid is loss of life and property due to these kinds of failures, these kinds of catastrophic events. What we basically want is, before a crack grows along the length of the pressure vessel, we want it to grow through the thickness so that the pressurized fluid inside starts leaking out of the cylinder and gives us a warning that something is wrong, something is going to happen, and we have some time to take corrective action. So that is the idea of leak before break. The crack should grow through the thickness rather than along the length of the pressure vessel first. Okay, now let us take an example of how this can be achieved. Before doing that, let me talk about uh, another handbook stress intensity factor case. This time for a three-dimensional crack. So here is a plate. This is a thick plate of thickness T, width 2b, subjected to remote load sigma naught, and there is a crack here which is thumbnail shaped. It is a semi-elliptical crack with one major axis 2c and one minor axis equal to major axis equal to c, and semi minor axis equal to a. So this is the crack. So if you look from here, this is how it will look. If you look from this direction, this is how it's going to look. This is the crack slit. This would be 2c, and you will have sigma naught. This, from this view, it may look like a Griffith crack, but remember this is actually a semi-elliptical crack. If Griffith crack goes through, Griffith crack would have been through this specimen. Griffith crack would have been like this. This is a semi-elliptical crack which goes up to some depth A and then stops. Okay, so in a pressure vessel, uh, what happens is that uh, this kind of a flaw, if it's there in the walls, it starts growing. It becomes larger and larger in size. Then when it reaches very close to the other surface, then it suddenly snaps and bridges this small gap here. So this is from, if you look at from the top, this is how a growing crack would look like. This is the initial flaw. Then after some time, after you have pressurized, after you increase the pressure a little bit, it grows to here. More pressure, it grows to here. Finally it reaches here, and then it's as good as completely bridging the thickness. Once it's here, it just snaps through this rest of the ligament. So this crack is as good as a crack that has completely breached the thickness. So this is just an observation. So what we are going to do is we are now going to look at the stress intensity factor of this crack. And what are we going to look at specifically? Specifically, we are going to look at how the stress intensity factor depends on A by T. That's the first thing, how it depends on A by T. How it depends, so thickness to depth ratio of the crack. How it depends on the ellipticity of the crack, that is A by C. A by C gives you the ellipticity of the crack. A by C equal to 1 is a circular crack. And also how the stress intensity factor varies according to this angle phi that we measure from say this end. So phi equal to 90 is this point, phi equal to 0 is this point, right? So basically what we want the crack to do is to grow preferentially along the phi equal to 90 direction rather than grow along the phi equal to 0 direction. So we have imagined that this is the, okay, there's one thing that we have to understand is this result taken from this paper is actually for a finite thickness plate. So this is a flat plate, but we are applying it to the case of a cylinder where we are assuming that the cylinder has a very large diameter. Okay, the cylinder is like this. It has a curvature, of course. Here is the crack, but this diameter of the cylinder, which we measure from say the center here, this diameter is large, so that in the limit that r tends to infinity, this cylinder, the crack in the cylinder is nominally similar to the crack in this plate. So this situation is almost same as this situation. So the solution that these people gave in 1979 for stress intensity factor variation along this crack front is what can be used even for a semi-elliptical crack in a pressure vessel with a large radius. So that is the connection that we are making. The pressure vessel is subjected to pressure from inside. Similarly, this will be subjected to pressure from here, because this actually is a curved plate uh, dressed up as a flat plate because the radius is very small. And then this crack is a mode 1 crack because it's subjected to sigma theta theta at these two ends. And sigma theta theta, as we know, is pressure R by T. So this stress has to be replaced by P naught R by T in case we use the flat plate equations to simulate the curved plate situation. For the flat plate, this is the stress intensity factor that is given. Now, this stress intensity factor is given in terms of sigma naught. Oops. It's given in terms of sigma naught, which in our case is P naught R by T. So P is the internal pressure, P naught is the internal pressure. A is the length of the crack, A is the depth of the crack, and then there's this function of A by T, A by C, and phi. These are the non-dimensional parameters in this problem. So these functions are plotted through finite element simulations. So in this case, functional forms of this function is not given, but in this paper, several graphs are plotted for various values of A by T and A by C uh, to tabulate this function. So this function is known from finite element calculations. This is a constant factor. Q is an elliptic integral, so its values are known for a given ellipticity of this crack, and this gives you k1 as a function of phi. So as you walk along the crack front, the k changes. The point with the highest k is the point that is going to reach the fracture toughness K1C first. So that's where the crack will start its first move. As soon as it moves, its A by C is going to change, its ellipticity is going to change, and therefore we have to again see which is the point that has the highest stress intensity factor after it has moved. So we have to track it down like that. So now let us try to see how we can design it for leak versus break. So here are the finite element results for a crack of A by T equal to 0.8. So what we are basically assuming is once this crack has reached A of about 80% of the thickness, so this is your A, and once A by T is about 0.8, then this snap through happens, and this A by T equal to 0.8 is the limit after which we cannot stop this crack anymore. So this is A by T 0.8 is almost same as A by T equal to 1. So we design it for A by T equal to 0.8. So let us design for A by T. Let us look at this function f for A by T equal to 0.8, and we also start with some ellipticity ratio. So A by C equal to 0.4 is A by C is equal to 0.4 is the initial estimate of the ellipticity of the crack that exists without detection. Now let us look at this specific example and see how the stress intensity factor varies as we increase phi from 0 to 90 degrees. Okay, so phi is plotted here, and this factor which is k1 divided by this whole quantity, this function is plotted on the y-axis. So this is actually your f, A by C, A by T, and phi, and this is the curve for A by T equal to 0.8, and we concentrate on the curve for A by C equal to 0.4, and this is the curve that we should look at. This is our f. This is the f for our crack, and as we can see that this is maximum at phi by 2 phi by pi equal to 1, that is phi equal to pi by 2, which means it is maximum at this point. So for a crack with an ellipticity of 0.4, C by A equal to 0.4, the maximum stress intensity factor occurs at this point. So as you increase the pressure, this point would reach K1C first, and the crack will propagate along this direction first. And here Q is a complete elliptic integral of the second kind, and its value depends on the value of A by C, and it is equal to 1.151 for A by C equal to 0.4, which is our case. Okay, so now if this is the case, then uh, if a by c is equal to zero point 0.4 and a by t equal to 0.8, the crack will become a through thickness crack when this function is equal to, if we take this value roughly, this function is roughly equal to 1.4. So f, which is this, is a by c, a by t phi is 1.4. We have done this for a by t equal to 0.8, which is not exactly through thickness, but as we said, that once it reaches very close to this boundary, it just snaps through. So a by t equal to 0.8 is almost is actually through thickness. So it has reached here, then it just snaps through and becomes a through thickness crack. So we have taken a by t equal to 0.8, and for a by t equal to 0.8, this factor is equal to 1.4. So just remember this 1.4, and that's when it becomes a through thickness crack. So uh, now this is its K1C. This is its K1C for the material, which we have measured from some other experiments and it's been given to us. And the design load is 910 MPa. That's the pressure that has been applied. And we have taken a factor of safety of 0.75 factor of safety to reduce the design load a little bit. So this is what we need to apply, and this is we have just reduced it a little bit using this from this equation. So using suppose k has reached K1C, it will happen at this point when phi equal to 90 degree, when this load is the design 75% of the design load. Q is 1.151. Using all that and using 1.4, we get the value of A at the point when K reaches K1C, and that value turns out to be 5.76 millimeter. Remember, this is for a by c equal to 0.4 crack, so the C for this case would be 14.4 millimeter. Now what does this mean? What it means is that you start with a small crack, and at some point of time this crack grows to cover 80% of the thickness. So this has grown to cover 80% of the thickness, and when it has covered 80% of the thickness, we consider it to be almost a through crack, and then this is 14.4 millimeter and this is 5.76, and the crack is almost equivalent to a through crack of width 14.4 millimeter, not 14.4, twice of 14.4, I think. Twice of 14.4, that is 28.8 millimeters. Okay, C is 14.4, so this length is 28.8 millimeters. Okay, so when the crack width 2C is 28.8 millimeters, it has covered 80% of the thickness, which is similar to a crack which is through and has a constant length of 28.8 millimeters. And this through crack is now a Griffith problem. So this through crack would look exactly like this. This is 28.8 equal to 2C, and you have the design load pulling it. So now if this through crack, once it forms the through crack, if it is able to grow in this direction, that means if this Griffith crack can grow catastrophically in this direction, then we have not satisfied the leak before break criteria, because as soon as the crack reaches 0.8% of the thickness, it will start growing sideways, and will cause failure along the length of the cylinder. Remember, this is the length direction of the cylinder, and the cylinder center is somewhere here. Okay, so we don't want it to grow along the length. So what do we do? How do we figure out whether it grows? We have to figure out what is the stress intensity factor for this case. The stress intensity factor for this case is equal to sigma naught root pi a, that is for the Griffith problem. And if this sigma naught root pi a is greater than K1C of the material, then this crack will start growing in this direction. So let us see how much this K1 is, whether it is greater than K1C for crack length 2A of 28.8 millimeter. And indeed we find out that for a crack length of 2C equal to 14.4 millimeter, the K would breach the fracture toughness, which is given here, of the material. So sigma naught root pi C, where C is 14.4, would be greater than K1C for the material. Okay, so if we use a thickness of this, we won't have a leak before break criteria. Now consider a crack of thickness of length 2C prime. Okay. And we want that when the crack grows to 2C prime, it should just touch K1 equal to K1C. The ones are missing here. K1 equal to K1C. And the design load, sigma naught, is equal to 0.75 sigma y. And if we do that, we get C critical equal to 9.1 millimeter. If C critical is 9.1 millimeter for a crack with C by A equal to 0.4, then we get A is 5.7. If we have this, then 0.4 into 9.1 is 3.64 millimeter. 3.64 millimeter is the thickness that we should have in order to assure that leak occurs first before break, so that when the crack actually breaks through the thickness, when it goes through the thickness, it is not eager to also propagate in this direction. It is not eager to propagate in this direction, and that we can ensure by having at least a thickness of 3.64 millimeter of the plate. So this is how leak before break designs are done in using linear elastic fracture mechanics, and this is one of the major achievements of fracture mechanics in pipeline design, pressure vessel design. Obviously, this is a simplified example. This is used linear elastic fracture mechanics. Most pipeline materials are ductile, so there would be a lot of plasticity also involved. So these calculations would get modified by the presence of plasticity, the presence of the fact that the crack shape also keeps on changing as it propagates. All cracks are not semi-elliptical cracks, and so on and so forth. But this is a simplified overview of how leak before break designs are, or fail-safe designs, fracture-safe designs are done in reality. So we will stop here for this week.